Welcome to our deep dive into the fascinating world of communication systems. From the simple telephone to the most advanced satellite communication, these systems form the backbone of our connected world. Today we will explore three critical modulation techniques: amplitude modulation, angle modulation, and quadrature phase shift keying. At the heart of any communication system lies the process of modulation, the method of altering a carrier signal to transmit data efficiently. Modulation transforms the message signal into a format suitable for transmission over a chosen medium, ensuring it reaches its destination with minimal loss and interference. There are various types of modulation, each with its unique advantages and applications. Let's start with amplitude modulation, or AM. AM works by varying the amplitude of a high-frequency carrier signal in proportion to the instantaneous amplitude of the message signal. This technique is fundamental in communication systems, particularly in radio broadcasting. AM has several variants, including double-sideband full carrier, DSBFC, double-sideband suppressed carrier, DSBSC, single-sideband, SSB, and vestigial sideband, VSB. Each variant offers a different balance between power efficiency and bandwidth. The modulation index, represented by M, is crucial in AM. It determines the extent of modulation and must be kept below 1 to avoid overmodulation and distortion. AM is power efficient for low-frequency transmissions, but less so at higher frequencies due to the large amount of power required by the carrier. Next, we have angle modulation, which includes frequency modulation, or FM, and phase modulation, or PM. In FM, the frequency of the carrier signal is varied according to the amplitude of the input signal, while in PM it's the phase that varies. Angle modulation is less susceptible to noise and interference compared to AM, making it ideal for high-fidelity audio broadcasts such as FM radio. However, it requires a larger bandwidth, as described by Carson's rule. Carson's rule estimates the bandwidth required for angle-modulated signals. For FM, the bandwidth is approximately twice the sum of the peak frequency deviation and the highest frequency in the message signal. This rule helps in designing efficient communication systems with optimal bandwidth usage. Finally, let's delve into quadrature phase shift keying, or QPSK. This digital modulation technique transmits 2 bits per symbol by changing the phase of the carrier signal. QPSK uses 4 distinct phase shifts: 45, 135, 225, and 315 degrees, to represent the 4 possible dibit combinations. QPSK is highly efficient in terms of bandwidth, transmitting twice as much data in the same bandwidth as binary phase. Shift keying, or BPSK. The use of gray code in QPSK minimizes the error rate during phase transitions, making it a robust choice for applications like satellite and cellular communications. A QPSK transmitter splits the input data into 2 streams, modulating them with 2 carriers that are 90 degrees out of phase. The QPSK receiver then demodulates the received signal, recovering the original data streams using a phase detector. In summary, modulation techniques are the cornerstone of modern communication systems, each serving unique roles. Amplitude modulation offers simplicity, angle modulation provides noise resilience, and QPSK ensures bandwidth efficiency. Understanding these techniques is essential for anyone looking to delve into the field of communication systems. Thank you for joining us on this journey through modulation techniques. If you found this video helpful, please like, share, and subscribe to our channel for more deep dives into the world of technology and communication.